Good afternoon, everyone, and welcome to the third Brookhaven Lab Research SLAM competition hosted by the Office of Workforce Development and Science Education. My name is Sharon Pepinella, and I am the lead for the SLAM competition and will be your MC for the afternoon. Over the past few months, we have 13 postdocs and early career professionals across 10 different B&L departments and divisions who have developed, practiced, and fine-tuned 3-minute talks about their research designated for a general audience. I would like to thank the participants for their hard work, their patience, and their perseverance in developing these talks, as it's no easy feat. Each of these contestants have had their talks dissected, often numerous times, by scientific, technical, communications, and educational experts to help them communicate their research with a non-specialized audience. We hope they found this to be a rewarding experience, especially as now they have the opportunity to highlight their impressive research for you all. At this time, it is my pleasure to welcome Dr. Aleida Perez, Manager of the Office of Workforce Development and Science Education, to deliver a few remarks.
As Sharon mentioned, my name is Aleida Perez, and we're very thrilled to welcome everybody to this year's SLAM competition. This is our third year running the event at BNL, and it's a great opportunity. And it's a great opportunity, a vehicle for our early careers staff to share their science, their research, and to a general audience that makes our science very much comes alive and accessible. I would like to just briefly say thank you to Sharon for the time in organizing this event and all the time spending with the participants and practices, to Joe for also being part of the competition and helping giving advice to the participants and how best to improve their presentations and so forth. To you all, good luck. Wish you all the best. And for the time and that you spend in preparing your presentations, the feedback and all that, right? It's kind of thrilling and exciting. And so thank you for that. And to Mary, Lisa, Stephanie, Martin, and Ann for taking time to be a judge for today. So with that said, thank you all.
Thank you, Aleida. Before we jump into the talks, I want to extend my sincerest thanks to laboratory leadership for their continued support of this event. I also want to extend a special thank you to communications specialist Joe Gettler from the Stakeholder Relations Office, who worked closely with me over the past few years to help develop and evolve the SLAM competition. I would also like to thank Tom Kubley from the Collider Accelerator Department, as well as our inaugural SLAM winner, Daniel Marks from EIC, who provided valuable feedback and insights for our participants during our SLAM practice sessions. Of course, a big thank you to our panel of judges for recognizing the value in this type of event and taking the time out of their incredibly busy schedules to participate. And I'll speak more about our judges panel in just a moment. We appreciate the scientists, the supervisors, the mentors who have supported our participants' research and technical projects, as well as their participation in today's event. And of course, a big thank you to all of the staff in the WDSE office, without whom this competition would not be possible. So now I would like to give you a little bit of information about how this competition is going to work. So we have our 13 SLAM competitors who will come on stage to give their 3-minute talk. In between each talk, we will have audience participation trivia questions. So where's Cindy? There she is. So Cindy has the microphone. So I will read each question. During the, following the reading of the questions, I will have 4 multiple choice answers. You must wait until I read each of the multiple choice options before you raise your hand. Once that happens, the first person that Cindy sees will get the microphone, and the first correct answer will get a prize, which is this lovely Brookhaven National Laboratory smiley face pen, which lights up. Good stuff. So So you know, our SLAM participants, when they are giving their presentations, they will have a slide behind them. The focus of the SLAM talk is on the content and the presentation. So they are not allowed to add animations into their slides. They are not permitted to do rap or play a musical instrument on stage as well. So there will be no bells and whistles that go with their talks. Following the end of the SLAM competition, we would like to invite you into the lobby for a 30-minute reception with light refreshments, during which time the judges will deliberate. You will also, during that time, have the opportunity to participate in the People's Choice selection. There will be a QR code on the screen at the end of the competition, or you can use the QR code on the agenda that you received when you came in the auditorium. That judging will open at 2:30 and will close at 3 o'clock. So you can vote on who you feel the best competitor is for the competition. Following the reception, you were invited back in here at 3 p.m. for the awards ceremony, where we will announce the winners and give them ridiculously large novelty checks. They do receive cash prizes for this competition. So our third place winner will receive $500. Our second place winner will receive $1,000, and our first place winner will receive $2,000. And you, the People's Choice audience, will vote for someone to receive the People's Choice Award of $250. This can be one of the first, second, or third choice winners as well. Additionally, one of our top winners will be selected to represent Brookhaven Lab at the National Lab SLAM competition, which is tentatively scheduled for the spring of 2026. All 17 national laboratories send one winner to this competition, and these participants present their talks on Capitol Hill in front of congressional delegates. On to our judges. So this year we are very pleased to have Ann Emmerich, our Deputy Director for Operations within the Director's Office, Lisa Miller, our Senior Biophysical Chemist at USCEO in the National Synchrotron Light Source 2, Aleda Perez, Manager of the Office of Workforce Development and Science Education, Stephanie Rucco, Principal Media and Communications Specialist for the Media and Communications Office, Mary Rogers, Small Business Liaison Officer for the Procurement and Property Management Division, and we have a very special surprise guest, Martin Schoonen, the Interim Deputy Director for Science and Technology. So we're very pleased to have our panel of 6 judges. As you can see, this is a mix of lab leadership, communication specialists, scientists, outreach, business relations, and so on. So we have a broad range of individuals who will be reviewing our SLAM participants today. So what are they looking for in this competition? This is essentially the criteria that the judges will be grading the SLAM participants on, including the quality of the scientific content, the clear logical sequence of their talks, the enthusiasm that they bring to the stage, the avoidance of scientific jargon, the ability of the speaker to engage the audience, their stage presence, although they can't juggle, as you can see here, as well as the appropriate use of that allotted 3-minute time. With that, I would like to introduce our first speaker. Our first speaker is Ananya Chattaraj from the Center for Functional Nanomaterials. Ananya is a secret animal whisperer, as in she likes to talk to any animal she finds. And while she believes science is serious, she tries not to be, even sneaking into empty children's parks to enjoy all of the rides. Today, Ananya is going to shine light on the quantum materials of tomorrow. Please welcome Dr. Ananya Chattaraj.
Quantum computers have the ability to give solution of a single problem simultaneously, but classical computer can do so once at a time. What drives quantum computer? A qubit, a tiny fragile component, which is considered a heart of a quantum computer. Classical computer works based on the classical bits, like a globe has a 2 pole, 0 and 1, north and south pole. But qubit can relay any point on this globe. This is how quantum magic works. But this qubit fails. This qubit fails not due to the complicated math. This fails due to the material imperfections. A speck of contamination, a rough surface, a oxide layer, a misplaced of atom. Like you are building a house with cards, castle, and just misplaced of one card, your whole structure collapses. What we can do to make a good qubit? Recently, Co-Design Center for Quantum Advantage at Brookhaven National Laboratory used tantalum, one of the hard metal, for making qubit. We at C2QA researchers and our Princeton collaborators made good qubit with tantalum. We have pretty much good result, but we not achieved yet actually we wanted, because still tantalum is imperfect. What we can do to get better surface or protect the material? We encapsulate it, exactly, like building a sand castle and sealing it under a dome. But how we'll understand this dome is perfect and working perfectly, protecting the tantalum material? Yeah, we shine light onto it. Yes. Brookhaven, we used National Synchrotron Light Source 2. We used X-ray, which is million times brighter than the sun, to probe our encapsulation layer atom by atom. We not only used one technique, we used several X-ray-based techniques. And here, the real hero is the detectors, which catches all the signals coming from the materials and give us the mystery of the encapsulation layer and the protected tantalum. It gives us the result which human eye can't. So these detectors are very useful to reveal the material property and encapsulation layer. And this how we work. At Center of Functional Nanomaterials, we prepare tantalum, encapsulate it with platinum. At NSLS, we reveal the material property and the encapsulation for making a better qubit and quantum computer. If we make a better material, it don't just give a better qubit. It will give us a better quantum computer. Because in the end, quantum computing is very simple. If we master the materials, we'll master the quantum.
Thank you, Ananya. Is everybody ready? Because it's trivia time. This question returns for the third year in a row because it keeps stumping the audience. So, what is the largest Office of Workforce Development and Science Education community event? Is it A, Science Bowl, B, Maglev, C, Science Fair, or D, Bridge Building Competition?
No. No. He answered it last year. It's not it. Oh, here's one. No.
Really, nobody up there? D, bridge building.
Bridge building is incorrect.
Science fair? Science fair.
Science Fair is correct. On to our second trivia question. What is the most streamed holiday song to date? Is it A, White Christmas, B, Feliz Navidad, C, Jingle Bell Rock, or D, All I Want for Christmas Is You? We have a very shy crowd this year.
D.
D, All I Want for Christmas Is You, is correct. So White Christmas is the best-selling single of all time, but All I Want for Christmas is the #1 most streamed. Our second speaker is Dismas Choge from the Accelerator Facilities Department. Dismas enjoys volunteering as a science teacher in his rural community to motivate students to embrace STEM subjects. His own love of STEM goes back to his primary school days when he used to chase a tiny sunspot onto a classmate's arm with a pocket lens. Now, he's scaled up that trick, but instead focuses laser beams just not on people. Today, Dismas will focus on the blink that breaks, inside ultra-fast laser-induced damage. Please welcome Dr. Dismas Choge.
Ultra-fast lasers are special type of lasers that produce small, short paths of light that last 1 trillion times. That lasts 1 trillion times less than a second. These lasers are key to generating life-saving radiations for cancer treatment in a more precise manner. And they do so by accelerating electrons to nearly the speed of light. Let me tell you what happens inside a laser accelerator. When an intense laser beam is pushed through a sea of electrons, it creates behind it a wake as it propagates. Some electrons are trapped in the resulting plasma bubble, and they get accelerated to approach the speed of light within a short distance. The consequence of this is more compact laser accelerators, and this is the promise of the future laser particle acceleration. Apart from the intense laser beam, the true heroes in this promise are the optical components, for example, the mirrors that steer it and the lenses that focus it. These components are the building blocks of laser particle accelerators. However, there is a challenge. The energy scaling and performance of such laser accelerator systems are often limited by the amount of energy an optical component can withstand before it fails, leading to system shutdown and expensive replacements. In my research, I use ultra-fast lasers to precisely measure the damage threshold of optical materials. In particular, I expose optical materials to intense laser pulses. And just like a detective, I look out for the signs that the material is about to rip apart and render it useless. I developed a simple yet robust approach that allows to gather as much information as is possible from a single laser shot. I also make use of microscopes to look at the scars created by the intense laser pulses in an attempt to unravel the unseen physical processes that led to the damage. The results are within reach in shaping the technologies of the future laser particle accelerators. By combining highly tolerant materials, it is possible to push the boundaries of the accelerating gradients of the future laser accelerators to make them more powerful and more compact. Imagine a world where cancer therapy machines are the size of a ping pong table and can fit to nearly every hospital in the world. With this research, we can change the world in a split second. Thank you.
Trivia time again. Approximately how large is the Rick ring in circumference? Is it A, 1.4 kilometers, B, 3.8 kilometers, C, 6.7 kilometers, or D, 8.0 kilometers?
B.
B, 3.8 kilometers is correct.
Thank goodness. I was worried. Bosses are here, you can't go back wrong.
I was thinking maybe putting it in kilometers instead of miles would throw people off, but. Next question. What common holiday spice is actually the dried bark of a tree? Is it A, nutmeg, B, cinnamon, C, cardamom, or D, ginger?
Cinnamon.
B. B, cinnamon is correct. Our next speaker is Stephen Farrell from the National Synchrotron Light Source 2. Stephen is a local, born in Ridge, New York, and he knew he was destined for B&O even as a toddler, as he visited his first B&L open house at the age of 18 months. Stephen is an avid hiker and has climbed mountains all around the world, including as far away as Japan. Today, Stephen is bringing us to new heights as he shows us how he's lighting the way to new energy. Please welcome Dr. Stephen Farrell.
Nearly 130 million people live along our coasts, hundreds or thousands of miles from the natural gas sources we rely on for most of our energy. Compressing natural gas for transport is costly, and unused gas that can't be stored is often just burned off, wasting over $2 million a day in the US alone. If this gas was rather a liquid, we can move this energy with ease. My team at Brookhaven Lab has been changing the way we use natural gas, which is mostly methane, by transforming it into a very useful liquid, alcohol. Alcohols are excellent as clean and convenient liquid fuels, among other uses I won't get into here. We use special materials known as catalysts that assist chemical reactions, because turning methane gas into an alcohol like methanol is rather hard. Methane is stubborn. Too much energy, and it just burns into carbon dioxide. But too little, and nothing happens. Catalysts help to strike that balance and make rapid gas-to-liquid energy a reality. We have indeed made significant progress developing new catalyst materials that coax methane directly into alcohol without making carbon dioxide. But we need to tune them to be as efficient as possible. The problem we face is, often we know which catalysts work, but we have no idea how they work. So where do we even begin to improve them? That's why I study catalysts at the National Synchrotron Light Source 2, a facility that generates incredibly bright X-rays that are billions of times brighter than the sun, and yet invisible to our eyes. With X-rays, we can see down to the atomic scale how our catalysts behave in real time while they're making methanol. By studying how our catalysts absorb or scatter this powerful light, we capture split-second chemical changes, such as where methane sticks onto the surface of our catalysts, to learn what features are vital for transforming methane into methanol. We can then move on towards transforming our catalyst, modifying them by changing our size, shape, and composition of these materials based on their structure and based on our results. And then that gives us precise control over a critical energy resource we typically just combusted. Now, natural gas typically contains more than just methane, often containing contaminants like sulfur, which, even in tiny amounts, can damage catalysts and prevent them from working. Currently, such tiny amounts are tough to study, but with world-class upgrades to our synchrotron on the horizon that will increase brightness and sensitivity for the entire scientific community, we are enhancing our capabilities. And this way, we can move towards we can move towards developing catalysts that are more robust against critical contaminants like sulfur. By harnessing this brilliant light, we can move towards a new generation of cleaner, affordable, and more accessible energy delivered everywhere from coast to coast.
Trivia time again. Irving Berlin wrote this 1918 musical review while stationed at Camp Upton, the precursor to Brookhaven Lab. Was it A, Yip Yip Yap Hank, B, As Thousands Cheer, C, Mr. President, or D, New York State of Mind?
I'm not going to run. Safety first.
A, Yip Yip Yak Hank.
Yip Yip Yap Hank is correct.
Can you sing it for us?
No,
Sharon?
thank you. Which holiday plant relies on a parasitic relationship with its host tree? Is it A, poinsettia, B, holly, C, mistletoe, or D, amaryllis? Do they have the answer?
No.
Oh, it's C. C.
C, mistletoe is correct. Our next speaker is Sabrina Garrique from the Center for Functional Nanomaterials. Sabrina enjoys unwinding by crafting and sketching. Just hand her a pencil and paper, and she's happy for hours. She also moved from Germany to Sweden by bike to start her PhD, which taught her how to pack luggage like a pro. Today, Sabrina is unpacking how we can turn pollution into products. Please welcome Dr. Sabrina Garrique.
60% of the electricity in the United States comes from fossil fuels, which means every time you charge your phone or turn on a light, you're releasing carbon dioxide into the atmosphere. Carbon dioxide is classified as a pollutant. But what if we could take that pollutant and turn it into something useful? Turns out we can. Carbon dioxide can be transformed into carbon monoxide, which you might know as a toxic molecule, but it's safely used in the chemical industry for a lot of chemical processes. It's used to make synthetic fuels, textiles, paints, glues, and all sorts of things. This sounds great, right? Suddenly, carbon dioxide turns from a waste into a raw material. But it doesn't do that on its own. It needs another material to help the conversion into carbon monoxide. A material that's really good at this is rhodium, which is a noble metal. Sounds great, right? We start with a pollutant, take a noble metal, and we get useful products. However, there are two main challenges, which is why we aren't doing that yet. Challenge number one, rhodium does not only produce carbon monoxide, it also produces methane, which we just learned is much harder to handle, and it's also an even worse pollutant. The other challenge is that rhodium does not work forever. It deactivates over time. And since it's a noble metal, it's really expensive to replace. So, I try to understand why rhodium is making these two chemicals and how we can keep it stable for a time and stop it from deactivating. When you look at the literature, you find a very simple model. Single individual rhodium atoms make the carbon monoxide, while larger particles consisting of multiple atoms make the methane. So we teamed up with two collaborators who can make these two different types of rhodium and ran our first test reaction, thinking we knew what would happen. However, when we did our first test, we saw that the larger rhodium particles were also producing a small amount of this carbon monoxide, which completely contradicted this model that we find in the literature. I use advanced spectroscopy methods to study how the rhodium changes during the reaction. And what I can see is that these atoms rearrange really dynamically during the reaction. These individual atoms form larger clusters, the clusters grow, and under certain conditions, individual atoms can break off. We're currently working on untangling these different phenomena, trying to understand which of them facilitate the reaction and which of them hinder it. Because if we can keep rhodium in its most stable form, we can make the conversion of CO2 to methanol more affordable, allowing us to turn this major pollutant into products. Thank you.
Trivia time again. This isotope, first developed by Brookhaven Lab in the 1950s, is responsible for 80% of the nuclear medical imaging procedures performed throughout the world. Is it A, strontium-82, B, actinium-225, C, germanium-68, or D, technetium-99?
Let me give someone else a chance. You answer.
It's B.
B, actinium-225 is incorrect. Where are you going?
It's D, tactinium.
D, technetium is 99 is correct. All right, ready for a holiday question? Approximately how many cranberries are needed to make 1 can of cranberry sauce? Is it A, 50, B, 200, C, 350, or D, 1,000?
I think it's C, it's 350.
350 is incorrect.
I'm in a room of brilliant people. Nobody. Pete, you Googled it?
I know, what size of can is it? D?
D, 1,000 is incorrect.
All right, Pete.
And I forgot to tell you, if you guessed
B, 200.
B, 200 is correct. And I forgot to mention, if you guess incorrectly 3 times, I get to keep the pen. Our next speaker is Raman Kumar from the Instrumentation Department. Raman finds everything interesting, which seems like a good feature in a scientist, and has an extremely wide research moat covering various disciplines of engineering and physics. Today, Raman is dropping that drawbridge and inviting us on a quantum quest into dark matter. Please welcome Dr. Raman Kumar.
Everything we have ever known or seen is only 15% of what's present in the universe. The remaining 85% is dark matter, and we still don't know what it is. What we do know is that it's everywhere. It shapes how galaxies rotate and how cosmic structures form. And as we go on about our daily lives, dark matter quietly passes through all of us. For this very reason, it's incredibly challenging to detect dark matter directly, because it barely interacts with anything we have ever built. So we need new kinds of sensors, ones that are ultra-sensitive. And this is where quantum technology comes in. Atoms make some of the best quantum sensors. At Brookhaven National Lab, we are working towards developing a new kind of quantum sensing technology based on ultra-cold atoms. Atoms cool down to nearly absolute 0 Kelvin temperature. Cooling them down is essential to make them stable, quiet, and almost noiseless. Any tiny disturbance from passing dark matter can show up as a shift in their energy levels. But we don't stop there. To boost sensitivity, we plan to place them inside tiny mirror structures called optical cavities. You can think of an optical cavity as 2 curved mirrors that trap light between them. When an atom sits inside a cavity, the interactions become dramatically stronger, and we get a powerful amplification in sensitivity. And there's one more advantage. With cavities, we can place multiple atomic sensors at different geographic locations, connect them using optical fibers, and make comparative measurements. Any real dark matter signal will affect all the sensors at the same time, and that's exactly the kind of shared signature we'll be looking for. Over the last year, my team and I have made incredible progress. Using state-of-the-art facilities here at Brookhaven, we have developed some of the world's best cavity structures. These cavity structures are extremely precise, and their curved surfaces deviate from a perfect mathematical sphere by only a few nanometers. To put that in perspective, that error would be like changing the height of Empire State Building by the thickness of a penny. And now we are rapidly moving towards integrating these elements with cold atoms in what could become some of the best dark matter sensors ever built. Ultimately, The hunt for dark matter is a reminder of how little we really know and how much is out there. It has the potential to transform our understanding of science, revolutionize technology, and reveal entirely new hidden layers of reality.
Back to trivia. The growing collaboration for the Electron Ion Collider, or EIC, includes over 300 scientific institutions from how many different countries around the world? Is it A, 11, B, 15, C, 28, or D, 41?
It's C, 28.
C28 is incorrect.
D41.
D41 is correct. Holiday trivia time. Which reindeer is generally considered to be Santa's fastest? Is it A, Dasher, B, Blitzen, C, Donner, or D, Rudolph?
Come on now.
Over long distances or
Think generally.
You want to take a guess?
Dasher?
Dasher is correct. So while Blitzen means lightning, Dasher is actually referenced most often as being the fastest reindeer. Our next speaker is Christian Lackner from Environmental Science and Technologies. As a kid, Christian was terribly afraid of thunderstorms, but he's done a 180 because now he studies them. He even goes storm chasing, which has taken him to all of the states in Tornado Alley. Today, Christian's bravery assists him as he's unraveling the role of tiny particles in big storms. Please welcome Dr. Christian Lackner.
We've all been there. You plan a barbecue or a day at the beach. The forecast promises perfect weather, but then, out of nowhere, it starts to rain. And while that's annoying, bad forecasts can lead to consequences that are far more serious. Farmers caught off guard by flooding can lose their entire crop. Utility companies, unprepared for strong winds, can end up with downed power lines and no way of delivering power to you. People can even lose their lives when bad forecasts trap them in the path of floods or tornadoes. My research at Brookhaven National Lab is focused on a weather event that is notoriously difficult to forecast and dangerous: thunderstorms. At their core, thunderstorms are big bubbles of hot air rising through the atmosphere like giant hot air balloons. The faster the air shoots upward, the stronger a storm becomes. What powers this upward rush is a basic physics principle. When water vapor turns into liquid droplets, it releases heat. That heat fuels the storm, driving air upwards even faster. I study how this heating is influenced by tiny particles in the air, like dust or wildfire smoke. Clouds cannot exist without these particles. They're like little seeds. Every droplet in a cloud needs to form and grow. So maybe more of these particles could help turn water back into liquid faster, boosting the heating inside storms. But does that mean that fewer particles make storms less dangerous? Proving this is complicated. A storm's strength depends on a tug of war between temperature, humidity, wind, and particles. The Department of Energy deploys instruments around the world to measure these atmospheric components. I use those large data sets to train an artificial intelligence model, which learns about the complex relationships between everything that influences storms. From this knowledge, it can infer how much particles really impact the strength of storms. Surprisingly, I found that, that particles change the strength of the storms that we measured by only a few %, much less than many scientists used to think. A misunderstanding like this can lead to less accurate forecasts. Now, the next step is to use this result from the real world to improve the simulations that make weather forecasts. So, when you check the weather on your phone later, remember that forecasts are a work in progress, and researchers like me are working to make them better, to protect our food supply, our power grid, and maybe even save your life.
Thank you, Christian. Trivia time again. Established in 1946, this was named the first official U.S. national laboratory. Was it A, Los Alamos National Laboratory, B, Oak Ridge National Laboratory, C, Lawrence Berkeley National Laboratory, or D, Argonne National Laboratory?
It is D, Argonne National Laboratory.
Argonne National Laboratory is correct.
Good thing you got that right.
B&L was not close behind. Now, the other three were facilities that existed ahead of time, but they were not officially designated or renamed as national laboratories until later.
Question.
Holiday trivia. Holding 7 candles and often made of wood, the Kwanzaa candelabrum is called A, menorah, B, vela, C, kerza, or D, kinara? This will be your redemption question.
You have to sing it. Sing it.
Menorah.
Menorah is
there's a song.
incorrect.
Is it D, Kinara?
Kinara is correct for Kwanzaa.
Rosa.
Our next speaker is Wenxi Lao from chemistry. Unlike most chemists, Wenxi's lab has no beakers, no fume hood, and no explosions, which I hope would be the case in most labs. It's just him, a laptop, and a few very overworked supercomputers. Wenxi runs so many simulations that if they were weather forecasts, nobody would ever trust him again. Hear that, Christian? Luckily, molecules are less judgmental than people with umbrellas. Today, Wenxi is letting AI do the dirty work of clean chemistry. Please welcome Dr. Wenxi Lao.
Think about driving somewhere new without using GPS. You may have an idea of the direction, you follow the traffic, make a few turns, and hope you end up at the correct location. For most of the time, you can't get there, but you may stuck in the traffic, take a long detour, and ends up later than you planned. The trip works, but it's messy. Many chemical reactions are like that. They can find their way from the starting material to the final products, but without a good helper known as a catalyst. They can take a long detour, waste energy, and make a lot of side products. So catalysts aren't showing up in the final products. They just quietly guide the reaction through a cleaner and faster path. And they are crucial to make our everyday materials like the fuels, the fertilizers, and the clothes. So the problem is, it's very difficult to identify good catalysts because there are over 100 elements on the periodic table, and they can combine in countless ways and structures. So if we rely on trial and error, like make one material, test it, and get lucky or not, and repeat, we are basically driving without GPS on the enormous chemical landscape. And that's the dirty work of clean chemistry. At Brookhaven National Lab, my work uses artificial intelligence and machine learning to make that search smarter instead of just harder. We collect data from experiments and calculations, and we train AI to link the pattern on which the materials performs as good catalyst and which materials are not. Then AI finds a pattern that links the material's property and its catalytic performance. So now, instead of blindly testing over thousands of possibilities, we can ask AI to narrow the list down to maybe 10 best promising catalysts. And this strategy, in my research, has pointed us to better catalysts that can effectively convert CO2, the waste gas, to methanol, the fuel. And as we continue to optimize our model, we can move faster from the idea of greener fuels, cleaner fertilizers, and better everyday materials to a faster reality. And that's letting AI do the dirty work of clean chemistry. And that's what we are working toward to the future of Brookhaven National Lab. Thank you.
Back to trivia.
That's me.
Ready, Cindy?
Yes.
All right. Researchers at Brookhaven Lab and Stony Brook University built the nation's longest quantum network. How many miles does it span? Is it A, 25 miles, B, 42 miles, C, 98 miles, or D, 147 miles?
It looks like people want me to call on them. Start here.
It is E, 161 miles.
Really, Pete?
Pete's not allowed to answer anymore. It's gone. It's cut. Okay.
So apparently this has been updated since I put together this slide, so we're just going to move on to the next question.
Here we go.
Oh, sorry. I guess it's C. It's just a guess.
So last I knew, it was C, 98 miles, but Pete is telling me differently, so we are going to move on. You can still get a prize, though.
You get Pete's prize.
Pete, you're not allowed to play anymore.
No more. I was being nice.
The first artificial Christmas tree, developed in the 19th century, was made from which of the following? Is it A, empty wine bottles, B, dyed goose feathers, C, felted wool, or D, tin cans?
Oh my God. I'm going to guess C, felted wool.
Felted wool is incorrect.
B, dyed goose feathers.
Dyed goose feathers is correct.
I think she Googled it.
Our next speaker is David Park from Computing and Data Science. David was looking to be a girl dad, but ended up the proud father of 2 boys. And last year, he commuted over 35,000 miles, so you know he's dedicated to his work. Today, David is driving toward a new future, from brainwaves to robots in dangerous places. Please welcome Dr. David Park.
Would you volunteer to walk into a room filled with toxic radiation just to fix a computer? Most of us would say absolutely not. However, today, in nuclear facilities or disaster zones, people should enter those dangerous places. Imagine this alternative. On the left, a person is safe at home, just thinking and relaxing. On the right, a robot is walking into the glowing radioactive room full of equipment. The goal of us is simple to say, but hard to do. Have the human on the left, and only send a robot to the radioactive room. How do we do this? We are building a brain reading machine using artificial intelligence, or AI, and electroencephalography, or EEG. EEG is a set of tools that listens to the tiny electrical whispers of your brain. Using this tool, a person can sit in a control room wearing a cap of electrodes and then imagine an action. Swap that computer card or turn that knob. Your brain creates patterns of activity, and our AI's job is to turn that pattern into something that a robot understands. My research focuses on this, reading the human mind. Interpreting brain activity is very hard. Our EEG device is very noisy at the same time. It measures the brain activity, but it mixes up with the muscle and the eye movements with nearby electrical devices. I handle the noise using two different approaches. First, I collect data from a huge pool of participants. This gives a large pool of examples so that our model can learn patterns that generalize to a single new person's brain. And then second, we use a large AI model as well. Prior work in large language models like ChatGPT shows that bigger models perform better often. Our large brain model thus achieves state-of-the-art performances in several benchmarks and tasks, including 80% accuracy in a motor imagery task, that is, predicting from the human mind to see where the robot has to go next. That is brain decoding, turning patterns of brain activity into the precise robot commands so that in the future, only our thoughts, not our bodies, have to enter dangerous places.
Thank you, David. Back to trivia. This database was established by Brookhaven Lab in 1971 and has made significant contributions to the field of structural biology. Is it A, PubMed, B, GenBank, C, Protein Data Bank, or D, iNaturalist?
Giuseppe, say it loud. See?
C, Protein Data Bank, is correct. The poem, "'Twas the Night Before Christmas," was originally published in the Troy Sentinel newspaper under what title? Is it A, A Visit from St. Nicholas, B, Upon the Magic Hour, C, Reindeer on the Roof, or D, A Yuletide Arrival? Tricky one.
A Visit from St. Nicholas.
A Visit from St. Nicholas is correct.
I think people are Googling answers.
Our next speaker is Hari Ravichandran from the Instrumentation Department. Hari likes to collect pressed pennies and coins. He also plays Indian classical percussion, so timing and rhythm are his thing, whether it's beats on a drum or signals in a chip. His timing is perfect for this evolving field, as today he's wiring the future of AI. Please welcome Dr. Hari Ravichandran.
Inside an AI data center, the systems powering everything from weather forecasting to natural language models, nearly half the electricity consumed is lost in the tiny metal wires that connect each chip. Not in the processors, not in the memory, but the wiring. The tiny wires that move data billions of times per second have quietly become one of the largest energy bottlenecks in modern computing. And as AI accelerates, the strain on the electrical grid of the country also increases. My research at the Brookhaven National Lab is helping find a solution. As AI models grow stronger, chips need more processors and more memory blocks, all generating more data that must be moved. And to connect all these components without making chips that are enormous or expensive, we need to make the wires even shrink faster than the processors themselves. Today's AI chips use copper wires about 20 nanometers in size, which is about 1,000 times thinner than a strand of hair. But at that scale, copper, the material that we have relied on for decades, cannot keep up. Copper wires become more resistive, losing energy as heat. They tend to fail more easily under stress and temperature. And ultimately, copper wires slow down AI systems. We need new materials and new ways to understand how these wires behave at an atomic level. And this is exactly what I do here at Brookhaven. At our clean room, I fabricate next-generation nanowires made from ruthenium, one of the most promising alternatives to copper, and look at them on how they perform. Using the X-ray imaging, the real-time X-ray imaging at the National Synchrotron Light Source 2, our team observes what happens inside these wires while they operate. Atom by atom, we look at voids forming, growing, and ultimately breaking the connection. Our results have pointed us toward solution. The ruthenium nanowires we build here last up to 10 times longer than copper wires. They seem to have a better and stable atomic structure and lose significantly less energy as heat. Improving the wire efficiency will have a drastic impact on the electricity consumption. Beyond the vaults of the AI data centers, it can also have a positive impact on the economy by reducing the stress on power grids, improving operational efficiency, and enabling a more sustainable computing. AI is already changing our lives. The future of AI will be shaped not only by faster processors, but also by the tiny metal highways that move all the information. And here at Brookhaven, we are building those highways one nanowire at a time.
Thank you, Hari. Trivia time. The Scientific Data and Computing Center at Brookhaven Lab currently stores approximately how much data? Is it A, 290 gigabytes, B, 330 terabytes, C, 400 petabytes, or D, 20 exabytes?
C, 400 petabytes.
400 petabytes is correct. According to the Oxford English Dictionary, how many different variations are there for the spelling of Hanukkah? Is it A, 7, B, 12, C, 19, or D, 24?
B, 12.
12 is incorrect.
It's okay, you tried, not like these other people. Daniel, take a guess.
D, 24.
24 is correct.
Woo! Daniel.
Our next speaker is Toshiro Sakabe from the Collider Accelerator Department. Toshiro likes wearing unique patterned shirts and really enjoys listening to Western and Japanese rock and techno music. Today, Toshiro's rocking that accelerator science as he analyzes forward-directed neutrons. Reveal more, heal more. Please welcome Dr. Toshiro Sakabe.
Neutrons are one of the fundamental building blocks of matter, everything we see throughout the universe. Neutrons are particles that are tiny and invisible. And as their name suggests, neutrons are electrically neutral. They have remarkable abilities that allow us to explore the hidden inner world of materials. They can reveal hidden structures that X-rays cannot. This makes neutrons powerful tools for inspecting infrastructure, for studying advanced materials, and even for treating cancer. For decades, researchers relied on nuclear fission reactors to supply beams of neutrons for their applications. But reactors are large, highly regulated, and limited in number. Today, researchers like me need more access to more neutrons. My research team is developing a next-generation compact accelerator-based neutron source. We already specialize in producing intense beams of heavy ions. We hold several world records for heavy ion current, including for lithium-ion beams. We are building directly on our strengths to develop a neutron source. Here is a basic idea. When a beam of lithium ions hits a hydrogen-rich target, such as a plastic film, it produces forward-directed neutrons. This is exceptional because neutrons have no electric charge and cannot be focused by electric or magnetic fields. I'm working to characterize and optimize this forward-directed neutron beam. I usually use simulations and experiments to ultimately guide the design of a future accelerator that is much smaller than a nuclear fission reactor. The accelerator I'm helping design would be less than 10 meters long and compact enough to be installed at many different facilities, including power plants, laboratories, and hospitals. This development will make neutron beams more accessible and easier to use across industrial research and medical applications. From inspecting critical infrastructure to treating cancer patients, neutrons will finally be available where they are needed most.
What government agency originally oversaw BNL when it was first established? Was it A, the U.S. Department of Energy, B, the National Science Foundation, C, the U.S. Atomic Energy Commission, or D, the U.S. Department of Commerce?
We have a special answer here from our house photographer.
C, U.S. Atomic Energy Commission.
That is correct. Holiday trivia time. In 1847, Hans Grainer started producing glass versions of what familiar holiday decorations? Was it A, snow globes, B, ornaments, C, hot cocoa mugs, or D, votive candle holders?
I'll say B.
Ornaments is correct. Our next speaker is Preetha Sarkar, from the Center for Functional Nanomaterials. Preetha has never met a dog that she didn't pet, and her family has a nickname for her, which is that of a famous Pokemon. I have to know, is it Pikachu?
Yes.
Now, did they call you Pikachu or Preethachu?
They call me Pika, but I was born before Pikachu was made.
Okay. Well, now we gave you a new nickname. Today, Preetha's got to catch all that knowledge while she's on her qubit quest, engineering the quantum revolution. Please welcome Dr. Preetha Sarkar.
The technology powering the computers we use today is not powerful enough to model diseases like Alzheimer's at a molecular level and help us find a cure. But a quantum computer can do that. The complex simulations that a quantum computer can perform will affect our lives directly, from materials engineering and energy production to data encryption and financial modeling. But first, we have big science hurdles to overcome. The kind of computer that sits at your desk in your office is called a classical computer. Some computations that can take a classical computer billions of years to do can be done on a quantum computer in a matter of hours. That's a bold claim, given that we haven't built an utility-scale quantum computer yet. But why is that? The answer lies in qubits. Classical computers encode information in bits, which can have two opposing states, like the two poles of a sphere, north and south. But a quantum bit, or qubit, encodes information not just in one position or the other, but anywhere on that sphere, all possibilities in between. The behavior of qubits can be linked or entangled to each other. 20 entangled qubits can store as much information as 136 million classical bits. But the qubits made today are far from perfect. They can crosstalk, degrade, and lose information over time. This results in quantum computers that give errors. These qubits also require massive cooling systems, since they work in a temperature that's colder than the cold vacuum of outer space. My research at the Center for Functional Nanomaterials at Brookhaven Lab focuses on building better qubits. I can make a class of high-quality superconductors called metallic silicides. Superconductors conduct electricity without losing energy and can be used to build qubits. The new qubit that I'm making using nanoscale electronic circuits of these metallic silicides will work at a temperature 10 times higher than previous qubits. So they require far less complicated cooling systems. They can also retain information longer. And lastly, we can make them using the same manufacturing techniques currently used in the silicon industry. A quantum revolution is approaching. But when it arrives, how we exploit it and the benefits we yield from it will all depend on the quality of qubits we make, and hence the material platforms we choose to use to build those qubits.
Thank you, Preetha. Back to trivia. The first chemical synthesis of a human protein was done at B&L. This protein was A, ribisco, B, collagen, C, filgrastim, or D, insulin.
D, insulin.
Insulin is correct.
Yay.
Due to water's molecular arrangement, typical snowflakes take on this shape. Is it A, pentagon, B, hexagon, C, square, or D, octagon? Well, that was a quick hand.
I'm coming.
Oh, it's B.
Hexagon is correct. That was a very confident answer.
It was, I believe her. I was giving her a pen anyway.
Our next speaker is Shaswat Tiwari from physics. Shaswat learned that he wanted to do physics after failing a physics course. He also doesn't drink coffee. He just puts some hot water in a cup and pretends to drink coffee with his mates. But today, there's no pretending when it comes to Shaswat's work in understanding the strong force. Please welcome Dr. Shaswat Tiwari.
As a theoretical physicist, I often get asked, is there any use to my research? Well, the short answer is yes. But to explain why, let me take you back to the beginning of 20th century. There were no supercomputers. There were no smartphones. In fact, we did not even understand what is going on inside an atom. As the century unfolded, we learned more about the intricacies of the atomic structure. Thomson detected electron. Rutherford detected the nucleus. And starting from there, there was a revolution that led us to the devices that we use right now. Then the message is clear. Fundamental science has the ability to unlock future technologies. Now, currently, we understand that the atom is made up of neutrons and protons banded inside the nucleus with electrons revolving around them. The protons and neutrons themselves are made up of quarks and gluons, which interact by the strongest force of matter. This force is 100 trillion times stronger than gravity and is aptly known as the strong force. Understanding this strong force, truly understanding it, is the key to the next technological revolution. And this is exactly what I try to do at Brookhaven Nuclear Theory Lab. I develop new technologies or new techniques which allow us to understand the experimental data that is generated by accelerators in Brookhaven, Jefferson Lab, and other facilities around the world using quantum mechanics and relativity. A particular method that I use, called factorization, uses this experimental data to generate a three-dimensional distribution of quarks and gluons inside the nucleus. This tells us how the strong force works and reveals how it binds everything together inside the universe. Now, the journey from fundamental science to technology is long. But as Albert Einstein said, with difficulty comes opportunity. A century ago, we did not understand electrons. Today, it powers our entire world. Maybe the strong force will do the same.
Thank you, Shaswat. Trivia time.
With Cindy.
Which of the following is not an element discovered at a national lab? Is it A, berkelium, B, livermorium, C, lawrencium, or D, alamosium?
I'm coming to you. Just take a guess. It's okay.
I'm going to guess B.
Livermorium is incorrect.
It's okay, you did good. Oh, we have a hand here.
Alamosium.
Alamosium is correct. Alamosium is not a real element. I made it up. Which of the following is the term for the fear of snow?
Scary.
Is it A, kynophobia, B, pagonophobia, C, pluviophobia, or D, nomophobia?
Floridian.
C?
C is incorrect.
Okay, it's all right. Coming over here. He knows the answer. You know the answer. You know this. You know this. Are you snowbird?
Nomophobia.
Nomophobia.
Nomophobia is incorrect.
Ooh. Hi. Hi. Do you have a guess?
A?
A, kynophobia is correct. So this comes from the Greek word for snow, kaion, and phobos for fear. And I know everyone's going to ask, so pagonophobia is the fear of facial hair, pluviophobia is the fear of rain, and nomophobia is the fear of being without your phone. Our final speaker is Sanji Wanaganethi from Nuclear Science and Security. Sanji's spice cabinet is organized like a color wheel, and she's developed such a precise sense of smell that her friends use her as a human expiration date detector for their questionable leftovers. Today, Sanji's using all her valuable skills to support cancer care to space missions. Why precise gamma ray data matters. Please welcome Dr. Sanji Wanaganethi.
We live in a world which is full of natural nuclear radiation from space, rocks, even the food we eat, like bananas. Our bodies have evolved to tolerate quite a lot of it. And in most cases, we can self-repair. But in the modern world, there are lots of applications and instances that involve nuclear radiation. Cancer treatment and medical imaging, nuclear reactors, and space exploration missions are few among those. All these applications involve high levels of radiation, so careful handling and shielding is essential. In order to determine the amount of medical isotope that should be administered to a patient, or how much shielding is required for a nuclear reactor or an astronaut, we must exactly know the amount of radiation emitted in these different scenarios. This is where my work at the National Nuclear Data Center comes in. I work with gamma rays, which is a type of nuclear radiation, and it is also a type of electromagnetic radiation. Gamma rays are much more powerful than microwaves or visible light. They are emitted from the tiny nucleus that lies at the center of each atom. Each nucleus emits a unique set of gamma rays, so it can be used as a barcode or a fingerprint to identify that nucleus. At the National Nuclear Data Center, I make high-precision gamma ray measurements of different isotopes using modern detectors, so exactly what and how much radiation emitted by those isotopes can be known. Recently, I measured gamma rays from 44 scandium sample, which was developed at the BLIP, Brookhaven Linac isotope producer, which is used for diagnostic medical imaging. The data will help the doctors to determine how much dosage they should administer to a patient. Additionally, fusion reactors are going to revolutionize the energy production in future. They are known to emit high energy neutrons. I study the effect of these high energy neutrons like shielding material, like tungsten, so proper shielding can be designed for future fusion reactors. Furthermore, I measured irradiated samples of materials that are commonly used in space at the NASA Space Radiation Laboratory in order to study the radiation damage on satellites and spacecrafts. So collectively, my research demonstrates the importance of making high-precision gamma ray measurements of different isotopes so they can be safely used for the benefit of mankind.
Thank you, Sanji. Last set of trivia questions, so warm up your arms.
This is your chance.
Developed at Brookhaven in the 1960s, this medicine is still considered to be the gold standard in treating Parkinson's disease. Is it A, levodopa, B, gabapentin, C, lisinopril, or D, aspirin?
Meet me halfway.
A, levodopa.
Levodopa is correct.
See that?
Thank you.
Last question. The New Year countdown ball drop tradition began in what year? Was it A, 1907, B, 1912, C, 1920, or D, 1931?
Claudine, would you like to take a guess?
D, 1931.
1931 is incorrect.
We have another hand here. You didn't say it, but.
C, 1920.
1920 is incorrect. One more guess and I get the pen.
1912.
1912 is incorrect. The correct answer is 1907, which is why I made it the first one. Feels weird to end on that.
I know. Tiebreaker.
I have no more questions. Pete, you got more questions?
Anybody want to sing Yip Yip Yapang? No?
So this concludes our competition. Let's have a round of applause for all of our contestants one more time. Welcome back, everybody, and welcome to our awards ceremony. So we're very excited to hand out our People's Choice third place, second, and first place awards. As mentioned before, each of these awards come with a monetary value, as I'll go through as we announce them. So let's get started. First, our People's Choice Awards. So again, this was audience vote for a winner. Our People's Choice winner will receive $250 is Toshiro Sakabe.
Thank you very much.
You can use that to block the sun on your windshield.
Can I take this? Thank you.
Our third place winner, who will receive $500, is Christian Lackner. Our second place winner, who will receive $1,000, is Stephen Farrell. And our first place winner, who will also represent Brookhaven Lab at the National Lab SLAM competition, is, oh, and will also receive $2,000. Preetha Sarkar. Let's have another round of applause for our winners. Once again, thank you everyone for joining us for our third Brookhaven Lab Research SLAM competition. We hope you enjoyed this, and we look forward to you watching the National Lab SLAM competition in spring of 2026. Winners, please remain behind so we can take pictures with you and the judges on stage. Thank you, everyone. Have a wonderful rest of your afternoon, a wonderful weekend.